who's in sales, but as technical as you can get while still being in sales. So is this looking at my like chest or something? Yeah, okay, there we go. Or up?
It wasn't until you stepped back.
Yeah. Oh, okay.
You're good now.
Okay. Well, I might move around, so it's definitely going to move. Oh well. So today I'm going to talk about bootc. So bootc is a project that Red Hat that we've been working on for a while now. That's been kind of incubating in our Red Hat communities right around Fedora and CoreOS and CentOS. And it's a way to deploy operating systems. So some folks have called it like the coolest thing to come to RHEL in a long time. So yeah, there's a lot of excitement inside of Red Hat about it, and so I hope that I can share some of that with you guys today. So see if this will work. There we go. Okay, so we're going to talk a little bit about immutable systems because bootc is an implementation of an immutable system. We're going to talk a little bit about what bootc is, the architecture, kind of how it works, and then some of the underpinnings, and then hopefully, if we have time, a little bit of a demo. So what is immutability? So immutable is not capable or susceptible of change. That's Merriam-Webster. That's not exactly what we want for our operating system. We don't want it to change never. We want it to change sometimes, but only when we want it to change, right? So CTO of ChainGuard, Matt Moore, has this quote about immutability not being about stopping change. It's about controlling and being intentional about the change that you're trying to make, right? So immutability being a property that we can leverage and use so that we can control how change happens on the system, right? And that's what we're really kind of looking at here with immutable systems. Now, there are references to a major motion picture franchise throughout the talk. I'll let you kind of figure out what that is. But if we kind of go back in time and look at stuff, okay, is anybody aware of what make sysb is?
Yeah.
Yeah, I knew you would say that. Anybody else? Yeah. So if you've run AIX, right, back in the day, this isn't a slide that I made. This is a slide that I found I stole from other Red Hatters, which I thought was funny they had make sysb on here. AIX is the only other thing, the only Unix-like, there are Unix that I've ever touched other than Linux. But yeah, so make sysb is a system backup utility, right? It makes a copy of the system. You've got Norton Ghost next to it, right? So backup and cloning were kind of our first approach to this sort of immutable system. Let's take a snapshot of that and be able to restore that snapshot, right? We can like get that point in time kind of system. Virtual appliances, kind of OVAs. Let's put everything that we need into this container, this VM, and not really kind of draw a box around it, and like we can ship that and we don't have to worry about what's kind of inside there. That sort of worked. Didn't work for everything. And then we have kind of image creation tools. So actually, I've got a good question because I couldn't figure it out and neither could Google image search. The one on the right is Packer, right? That's a P for Packer. I don't know what those other two are. Does anybody else know what those other two icons are? This is like, maybe they're nothing. Maybe it's just gibberish that somebody created, but
welder used to be called because it used to be named after some reptile.
Ooh, there you go. That's good. That could be. Okay.
If there were artificial intelligence,
so, okay, I didn't try, well, I don't know if Google image search, but like reverse image search on Google, right? It couldn't figure it out. So, yeah. Anyway, image creation tools, right? This was like, Packer, right? For example, you have a very rich configuration language where you can define how to deploy the system up front, right? You can do the configuration, you create a disk image, and then you can deploy that, right? So the disk creation utilities, the image creation utilities, coupled with automation, kind of give you a full system. You have some properties of immutability, but not everything. Unikernels are another thing. There's lots of unikernel-like projects, things that have tried to implement this idea of let's just shove everything, sign the whole thing, and deploy that, and that's all we need. And then immutable distribution. So we have things like CoreOS, right? CoreOS was one of the first ones, original CoreOS, not Red Hat CoreOS, right? CoreOS from the beginning around like 2011, 2013 kind of time frame. CoreOS came on the scene with a distribution that that bootstrapped itself in the initial RAM disk and then ran, and that was it, right? Like that was how you did the configuration. We have things like Talos Linux. Does anybody use NixOS or Nix?
Mix itself.
Nix a little bit. Yeah. Really interesting system. And then Talos Linux is another one. Anybody Talos Linux aware of that? It's another type of immutable operating system, really kind of designed around a very small footprint. So you don't actually even get SSH access. All of the configuration is done over an API. So you can't actually SSH onto the node, right? That's not like a thing. That's not like a feature that they have. It's supposed to be immutable. It's supposed to be declarative. So that's what we have to work on. That's kind of the, where we're coming from. Why do we want immutable systems? Well, we want that predictability, that reliability, right? If you're building a clone army, you want to make sure that they're all the same, right? If one is shorter than the others, that's a problem, right? And that's very easily noticed, okay? Okay. You want to simplify your management, right? We want this infrastructure as code. We want devils. We want pets, cattle, not pets, right? Like these are the sorts of things. We need to be able to scale ourselves. We need to be able to scale our management structures, right? And so we need some properties of immutability, right? Why are we doing immutable systems? Really, what we're trying to do is we're trying to separate that mutability part, your application data, from your immutable operating system, right? The things underneath, so that we can update the immutable pieces underneath the hood and keep your application data consistent on top, right? This will allow us to update the OS in an atomic fashion. We'll talk a lot more about that. Oh, also, point of order. If you have any questions or any comments or any statements or something like that, definitely raise your hand or just shout it out, like try to keep this as interactive as possible. Okay. Yes.
So, I'm an old timer, and before Linux was a thing, we had compiled kernels.
Sure.
And they were immutable because they were compiled kernels.
Mm-hmm.
Why are we reinventing the wheel? I mean, that is last of my bigger question, but
yeah, it'd be like a unikernel kind of approach. Yeah.
Power of Linux was Modcro, was you could install a module and modify your kernel, and that was Power of Linux that made it what it is.
Mm-hmm.
And so why are we trying to do that?
Yeah, it's a good question. I mean,
if I wanted to go back to so Sun OS and have it, I love it.
I mean, is Linux really? I mean, like it is a monolithic kernel architecture. It's not a microkernel architecture, right? You still have, you still have everything in the kernel, right?
You're not, but you can modify.
But you can modify, true. Yeah, sure. Yeah.
But like, I think the question, there's a difference between the kernel and being able to modify bin OS. Like, immutable in terms of file system, being able to go, hey, I broke it in, I can modify bin LS to give me super user privileges somehow.
I haven't had to into kernel already got that. Well,
Sure.
Kernel module says, okay, it's with the compiled kernel, you can't cache them one piece at a time. You got to do it all at once. So it's like Legos versus.
Things like Graph and K-Patch and Live Patch all exist that work in somewhat similar ways to the kernel's module system. Not really, that abstraction is really leaky. But we're really caring more about userland at this point, because once Except in very rare cases, once a given piece of kernel code has been loaded, it is typically not replaced until reboot. I put some, like 57 million asterisks after that.
That mod probe commands on our systems and unloaded and unloaded things.
And I will say, like, you also have things like CrowdStrike that are designed just to detect those kind of modifications. And they go, hey, no, changed, kill it.
There's also the catch that because Linux implements most of its drivers and modules, you don't have to load them all into the kernel image because the entire kernel image is loaded into memory at boot. And if you did that for every possible driver that that kernel could support, you would use so much memory it's not even funny. And so the kernel lazy loads modules on like desktop class systems. On embedded systems, it's really common to just turn off the module system. It's one gigabit option. It still calls itself experimental in gigabit. And if you're running on a phone, well, okay, that's a bad example. If you're running on that fancy new Arduino Q SoC, you probably don't have the module system loaded because it does come with a space penalty. And if you know exactly the kernel functionality you're going to need beforehand, if you're using something like Buildroot or Yocto, speaking of more potentially immutable distros, depending on how you're deploying them, you don't have the uncertainty of what PCI devices are going to exist here, what's going to be in the ACCI tables. Do I need the Airthros Wi-Fi driver versus the Realtek one versus the Intel one? Because I really don't want to load them all in there.
But my point is not about that. Why are we trying to reinvent?
I'd say that they are two separate problems.
Yeah.
And we want our cake and we want to eat it too, right? Like we want the mutability until we don't, right? Like we want the flexibility of being able to load whatever kernel modules we need in order to get the hardware functionality that we want in the operating system. But we don't want to add any more than we have to, right? We don't want to add anything that could be malicious. We don't want to, I guess we want both, right? We want full flexibility until we don't want any flexibility anymore. So, yeah. It's a good question. Okay, so when would you not want to use immutable operating systems or immutable systems in general, right? Maybe you're taking fire and you jump through a small hatch and you land and you discover that you're hoping you're getting to immutable operating systems, but you discover such an interesting smell, right? What an interesting smell, like Han Solo discovered, right? So that was my very crude segue there. So the mental model shift is, we're going to talk a lot more about this, but there is a difference in the way for bootc specifically how we look at runtime versus build time, right? Build time versus runtime. What you can do at build time and then what you can do at runtime are vastly different, right? There's a shift there. You have to start looking at maybe running all of your applications in containers makes a lot more sense. Even on top of your immutable operating system, because then you guarantee kind of this container space that you can modify whatever you need to, because you don't have access to modify things like user or opt on the host system. And you really have to start looking at configuration by declaration, like declarative configuration. We're going to talk a lot more about what exactly that means because it has a lot of implications on how we manage /etc going forward. It doesn't make sense in highly mutable systems, although there are a bunch of folks that I know at Red Hat who run their desktop, who run their laptop with bootc. They run an entire bootc system for their developer, for their workstation, and it works great. Every time they need to change something, they have to build a new image and then deploy that image. And so there's like that feedback loop. We'll get back to that. But generally, when you're looking at kind of these really like serious dev machines, right? You don't really want those kinds of properties. The legacy application risk, right? You have applications that are built with the assumptions of FHS, of the file system hierarchy standard, right? That was developed in, I don't know, the 80s, 70s, I don't know, when POSIX was developed, right? When? Somebody knows.
I know it's more recent than that, but I don't
know. Okay. All right, maybe I'm wrong. Okay. You don't have access to write to things like opt and user in a bootc system. And so software that requires that or that assumes that, right, you can run into some problems. And then that feedback loop, right? The feedback loop, the developer loop of making a change, right? Your hair's on fire. The server, you've got a problem with the application. All you have to do is modify this one file. But in order to do that, we all have to, we've built all these systems on top of our deployment systems, right? We've built configuration management systems, we've built deployment systems, we've built automation. And so in order to make this one change, you have to go through 3 peer reviews. 7 people have to say LGTM on a pull request, and then that has to get built and deployed to your fleet of systems, right? We've created these systems that make it a lot harder to do like a very quick management change on a system. And that's by design, but it is a shift in thinking, right? bootc necessarily, this type of immutable system necessarily demands a type of declarative system that works really well in kind of a a CI/CD system, right? Something that's going to you're going to push changes to like a repo, like a Git repo or something. You're going to let that build, and then you're going to deploy that to your systems, and then reboot, right? That's another part that we'll talk about, is that bootc requires a reboot in order to get to the next system. So, what is bootc? We've taken the idea of a container, right? Container, could be seen as an elegant weapon from a more civilized age, right? It's a system that we've used for a long time, that 10 years, it's forever, right? It's basically in tech, it's like forever, right? No, but it's got a standard packaging system. We've got the OCI standard. We've got standard registries. We've got the tools and technologies. Containers really have been incredibly pervasive throughout our tech stacks across all infrastructure. And so we've built up this system and tools and infrastructure of managing and maintaining containers. It gives you a lot of things like predictability of deployments and things like that. But really, it's this ecosystem that I think we're really trying to leverage here, right? We have all of these container scanning tools. We have all of these container deployment tools, these container registries. We've got lots and lots of options. And most people have something like that deployed in their infrastructure today. So if we can leverage this existing technology without creating something brand new, isn't that better? Isn't that great? Isn't that a good thing? And so what's a bootable container? It's basically just taking all those things and applying it to bootable containers, to containers that we can also manage as operating systems, and that we can deploy onto systems. It's a container that contains a kernel, right? It's kind of basic thing. And you may be thinking, this looks like a hunk of junk, but it's okay because it may not look like Munch, but she's got it where it counts. Okay. So, that's the thing. Okay. So it's nothing crazy, right? We're just taking, we're taking all of the kind of pieces of a container and we're adding a kernel. And we were talking about Anchor with somebody, I don't know, was it you? I don't know, somebody I was trying to Anchor with.
I don't think anyone name dropped it.
Okay. Yeah, no, I mentioned it. At Oak Ridge, we developed a system of using containers to build very similar, where we're shoving kernels into containers. So it's not like a crazy concept. It's just like it makes sense because we already have this tools and technologies available. So we're going to walk through the next couple slides, kind of walk through a build, deploy, and manage, and kind of what it looks like. But effectively, we're looking at, if you've ever seen a Docker file, if you've ever seen a container file, we're looking at you would build a container the same way that you would build a bootable container the same way that you build any other containers today, right? Yum install, DNF install, you do your package configuration, you copy in your stuff, that's it. There's nothing special, right? It's going to look the same. It's just going to be that from line is going to be a base image that happens to contain both a lot more than just a application container image, right? An application container image, like some of the Alpine images are like single digit megabytes, right? Like 9 megabytes for all of what you need to run Redis, HTTPD, whatever. These are like on the order of a gig, right? So they're a lot larger because you're containing a whole lot more, but it's all using the same concepts, right? There's not doing anything new here. It's just still containers. It's just we're a little bit bigger. Anybody try to pull an NVIDIA container with like the development environment? It's like everything and the kitchen sink. It'll do your laundry as well, right? Like it just has it's 4 gigs in size, right? It's just gigantic.
The SD card on your Jetson.
There you go. Yeah, yeah, exactly. Exactly. Those things are huge. Anyway, so yeah, it's a larger container image, but it still checks out. So if we're gonna build it, if we're gonna go hyperspace, that base image is really important. So it's not really too much here, but like we can't just use from scratch. We have specific like hard requirements that we need to build that base image from. And so we have that, it's in Fedora, right? So it's all just out there on some Git repo. But we do use some of the underlying tools called RPM OS tree in order to build a base file system. So you'll start to see we have bootc here, but we're going to layer on a couple of different tools and technologies as we go down the stack. Yeah.
So I noticed in your example container file, you were invoking DNF directs.
Yeah.
So is RPM OS tree just being used, say, in lieu of Anaconda here, and still producing a relatively normal user land?
So good question. We're not really using RPM OS tree at the bootc layer. So we're just doing our DNF installs. We're creating extra layers and all that stuff. When we actually apply that to the OS tree on the system, we're actually squashing all those layers. We'll see that later, but like we're squashing all those layers into a single OS tree commit. And so RPM OS tree doesn't really play a part in that anymore, right? It's we're kind of pulling that out and we're not really needing it anymore.
So you stepped away from RPM OS tree to just OS tree.
Exactly. And OS tree has really become kind of lib OS tree because we're not really using it as as kind of like a first class feature anymore. Yeah. It's really an implementation detail on the file system now.
And just because the things are great.
Yes, exactly. And then we'll talk about ComposeFS, which is kind of like where we're going now in the future. So if we look at building a bootable container, you build the container, like I was saying, you build the container the exactly the same way. We have so we have a couple of different best practices. One of them is running bootc container lint. Robert French will not be able to see this at the back of the room, but oh, okay. Well, yeah, okay. Yeah, you don't need glasses. Okay. So the lint will basically kind of let us know some of these potential issues that we may have with running with installing some of the stuff into a container and where we could potentially have some pitfalls in deploying that as a bootable container. So in this example, it's finding non-empty log files, it's finding container content that's in var that doesn't have temp file entries. It cares about those sorts of things because we're going to have because var is going to have to be writable during runtime. So we're doing a lint process to kind of identify any potential issues down the road with what we're going to have at runtime, having kind of a conflict between what's on disk in the immutable section and then what we're holding in the mutable section of var and etc. Yeah.
So do you have the same situation as you did in, say, Project Atomic, where var is effectively a link farm and is expected that the system infrastructure shall never touch it after installation?
No, it's a little different. var is just a writable area now, so it's a little different. Yeah.
So are we talking about writable in the sense of like overlay file system, or like NFS root as an overlay file system? What are you considering that?
Yeah, I mean, like what we'll have a so var and etc will be separate partitions that are writable and mounted on top, and then we'll have the rest of the system be immutable, and then we have to really care about how we update the writable portion. So we do care about what the data is. So it's not just quite like NFS root where we layer on like a tempfs or something like that and just don't care about it after that. We do care about what the content is, and we will update that content in certain scenarios. So we have this thing called a three-way merge where we kind of look at that, and we'll go into that.
So last one for this, like, where does, say, an RPM's post trans hit? What does it see for bar? I assume whatever's in the build environment.
Yeah, exactly. Yeah, it would be whatever's in the container build environment. Yeah,
Okay.
yeah. The script, the post-trans script.
Let's say, for example, you have I'm gonna pick on a commercially deployed product without naming it,
Okay.
that runs a series of migrations as part of the installation and relies on metadata from the previous version
Sure.
in order to determine what migration should be run.
That's a problem.
Yeah.
Yeah.
I
Because
think
we don't have runtime information at build time, right?
Yeah.
So yeah, that's like a hermetic build environment, right? So like we don't have access to actually what's on the deployed system at build time.
So would you say in this situation, bootc makes the assertion that it's the responsibility of an application as it is initializing to migrate state with no additional requirements?
Agreed. Yes. At runtime is when that initialization should happen, not at install time. Yeah, absolutely. Not at build time. That's right. Note in this example, we are adding the caddy.container, which is a quadlet container, right? Quadlet is basically a project that melds together Podman and systemd, right? So how can we have kind of native syntax for systemd that can understand how to run containers in Podman, right? As like system services kind of thing, right? So we're putting it into user, not Etsy containers. So there's a couple of different places you could put a quadlet container. You can put it into Etsy containers. You can put it in user share containers. But we're putting it in user share containers specifically because of this three-way merge. So with the Sith, there's always three, right? The master, the apprentice, and the modified configurate. No, okay. Anyway, so three-way merge. So we have this three-way merge where we do care about, like we were talking about, we do care about what's in the mutable portion. So in Etsy, if the Etsy contents were modified from the default, they're kept. We always trust what was modified at runtime first, right? But if the contents were not modified, if they're the same as what the previous configuration is, as we're moving to a new deployment, we will update them to the new default, right?
So you're saying that effectively user Etsy is an Etsy scale for Etsy.
User Etsy is Etsy scale. Yeah, sure. User Etsy is the read-only version of what Etsy would be on a new deployment, right? Yeah. So you could copy. So essentially, what you could do is, so like, say you had Etsy password and you accidentally modified it at runtime, you could copy user Etsy password to Etsy password, and now you're back to system default.
Okay.
And then we'll start managing it like the second line. When they're not modified, we'll update it. Yes.
Who keeps the permanent state? What?
This basically says the state is preferred at runtime, but will be kept up to date with the immutable state underlying.
Yeah, but who keeps that over reboots? Or is it not kept over reboots?
Oh, the disk, the local disk,
Okay.
right? So this all assumes, and this is a big caveat for the HPC folks in the room. This all assumes it's on disk, right? So we're not running diskless here in this case, right? Like this is all. I was talking with one of the engineers who runs bootc at KubeCon last year, and I was like, hey, we should think about diskless, and he was like, yes, and he made a GitHub issue, and a bunch of HPC people have commented on it, but nothing's actually been done. So it's a sad fact, but of all HPC things, I guess, really. But yeah, so this all assumes a writable partition on your local drive. And actually, it assumes that it owns the disk, really, and it can create those partitions as needed. Yep. So that's the three-way merge. So Etsy, Etsy is kind of the area where we have a lot of problems here, where we really have to think about this stuff. So things like invoking user add, right? We were just talking about Etsy password, right? You could start to create configuration drift in what your mutable state should be and what your immutable state is, right? So when you do an Etsy user add at runtime, it will add something to Etsy password, and now your like now you're detaching its password from the underlying system. And so that could be problematic because things could change over time with Etsy password that you want access to, right? When you install a new package that creates a new user ID at build time, you're not going to get that anymore because your Etsy password has now diverged. So there's a lot of different systems to deal with these sorts of things. The main one is like the .d directories, right? So being able to just drop in a configuration into .d. Basically, most systems have kind of adopted this pattern of configuration where you can drop in kind of a configuration snippet that gets, kind of pulled into the full configuration build out. That's a big thing. For specifically user add, I found system D sys users, which is another kind of similar drop-in configuration kind of system where you can specify what users should exist at runtime. And so that you would put that config file into place at build time, and then it would propagate into runtime. Yeah, I think that's it. Yeah, drop it. Yeah, sorry, I couldn't see my .d directory stuff. Yeah. Yeah, that's no moon. So, okay, another interesting kind of piece of our tooling infrastructure. This probably should have been closer to the lint process because it's similar to linting, but it's this idea of rechunking. So this is where RPMOS tree comes back to us. We'll see this a little bit in the demo if we have some time here at the end, but rechunking is the ability for we use RPMOS tree to use some heuristics across the what we see on the layers of the bootc image, and we will reorder and move around where the RPMs are and what layers those RPM files are, because we know what files go with what RPM because of RPM. And then RPMOS tree allows us to move those around in order to try to aggregate RPMs to layers that are closely connected and linked so that if one changes, it probably will change other ones around it, which really just allows us to limit the amount of data we have to pull on a new image creation, right? So when we create an image, say we create an image and we squash that image down to a single layer, and then we change, and that's a 1 gig image. And then we change one file, we add one line to, whatever, Etsy syslog.conf, and now we have to pull an entire gig, right? Like that's not cool. If only we could pull like a couple of kilobytes because that's all we did, right? So RPMOS tree rechunk is really kind of trying to make that a little bit better. And we'll see actually kind of what that looks like. But basically it starts separating sometimes individual RPMs into layers. There's kind of there's actually not an official limit of OCI layers, but there's a practical limit of about 128. That's generally, I think the system defaults to like 64 layers, but you could go up to that high. But yeah, it just tries to spread things out to make it, you can do parallel pulls that way of layers, right? And then it's really just an optimization. Getting back to that container native tooling, we have this container infrastructure already in our environment. So when you're building a Death Star, you want to be able to leverage all of the existing planetary, resources in order to do that build, or if you're building other types of Death Stars, maybe you built one and something happened to it, and so you built another one. Being able to validate and test that your Death Stars are okay. Anyway, yeah. So being able to validate and do kind of use the exact same tooling and infrastructure that you have already in place for your container environment is really, it's good, right? Hopefully we can get some speed up here because we already have this kind of infrastructure deployed to manage and maintain containers in our environment. So for deploying things, this is where we get into what we're talking about earlier about the file system layout. So pray I don't alter it any further, Chris. Okay, I'm altering the deal. Okay, so you don't have access to write to all of the file system like you do at build time. At runtime, we only allow access to write to var and etc. Oh, that's, I think somebody had a question about that, but var is not updated post install. So we only do the 3 merge on etc. But essentially they're separate partitions, and we use yeah, we'll talk about compose.fs later. So persistent data. So this is yet again another kind of caveat here, right? So classical data persistence rules all still apply, right? There's nothing magical about bootc that will maintain and persist your data across updates, right? So the example being like if you went from MySQL 5.7 to MySQL 8, and I don't know specifically, but let's say that the on-disk format from 5.7 to 8 changes, and you have a problem with your deployment of 8, it has updated your on-disk format, and then you try to roll back, you're going to have a bad day. You have a bad day, right? You still need to maintain your own backups. You still need to, snapshot persist that data in whatever way you normally do it, right? So there's no like kind of silver bullets here, right? These aren't the droids you're looking for. We have, for deploying the system, we have a couple of different ways. We'll talk about kickstarting as well, but we have image builder. This is kind of the newer way that that Red Hat has been pushing to deploy systems. It allows you to kind of build any type of image you would want, disk image or an ISO installer if you're doing bare metal. There is a GUI in the Podman desktop. There is a GUI on Cockpit. There is a CLI in the distributions of Fedora, RHEL, whatever. OS Build Composer is the CLI. So OS Build project kind of maintains all this stuff, but yeah, like you can create this stuff has been extended to allow for creating to transform an OS Build container into a disk image that you can deploy.
That's just different sidecar. In having
Sidecar.
yeah, where you have an image, the sidecar OS that's got a minimal OS, and then you add Docker units for all pieces parts.
I'm not sure what you're talking about.
I think you're thinking of flat car.
Flat car. Okay. So CoreOS was created like, I don't know, 2010s or something. They created a bunch of technologies, including CoreOS. They get bought by Red Hat in like 2016 or something like that, 2018. And Red Hat changes CoreOS to Fedora CoreOS, kind of retools that whole infrastructure. A fork of the original CoreOS comes out as Flatcar, right? Yeah.
So how does that entail into this?
I believe Flatcar is still around, and it's using the original way that CoreOS was doing things, right? So similar immutable system. I believe original CoreOS, and probably Flatcar was doing a single AB deployment patterns, right? So you had 2 partitions on disk. You deploy to one. You fill up that partition with your OS. You deploy into that, and then when you upgrade, you fill up the other partition, the B partition, with your new upgrade, and you deploy to that instead, right? So yeah, I mean, similar kind of paradigms, right? But the underlying technology is vastly different, right?
I guess you could say, in theory, you could deploy a bootc container in the same methodology that Flatcar does, but the on-disk format would be different. You'd have to make a bunch of tooling adjustments. Let's say similar idea, different implementation.
Yeah.
We have a couple of vendor tools that are just flat like deployments.
Mm-hmm.
And I don't care about any of the rest of the stuff. It really works, and that's all I care about.
Yeah, exactly. Yeah, sure. Yeah, solid tech.
Does reproduce it still use Flatcar?
Does what?
There's a product that was meant for shipping complex things as an OVA called reproduce it, and I believe it used to use Flatcar.
Oh, okay. I don't know.
It started out with Project Atomic, then moved to CoreOS, and
Mhm.
then I think it went on with Flatcar.
Okay. Yeah. Yeah. No, I don't know.
Okay.
Question. Yeah. So Kickstart, you can also deploy it via Kickstart. If you're familiar with the RHEL ecosystem or the enterprise Linux ecosystem of Kickstart, Kickstart is a it's like Debian pre-seed, I think. It's a way of specifying in a config format like what the installer should do to install the OS, right? You can see that there is no percent packages, right? Because we don't need that. That would be the traditional way you would add packages to your installation. Kickstart would handle like things like zeroing out the NBR, setting up your partition tree, that sort of stuff. And then it would start doing yum installs, right? It would start installing into an install root. Instead of that, what we have OS tree container where it just pulls container and does the necessary things that it needs to boot or to be able to reboot into a bootc container.
Or is that just base container?
No, yeah. So you can do pre and post, right? Okay. So that would be the tradition. I would guess that most folks, that's how they would do like something like secret preceding or things like that, right? If you need to add like some type of like, cardinal secret to your node after you deployed it, right? It would be like a post install, right? Yeah.
I was thinking of like Kickstart followed by immediate Ansible.
Yeah, sure. Yeah, you could do that.
Works well for us.
There you go. Yeah. Yep. Okay, so yeah.
So the ONDIS that this results in, does it result in an OS tree in a bootc OS tree environment on the disk of target host, or does it result in an environment that is the same file system that would be, without the trappings?
It is a OS tree commit on a file system.
Okay.
Yep. And then from there, it will reboot. It will do grubs, dynamic.
Yeah, the BLS.
BLS. Yes, thank you. And it'll boot into that. Yep. So management. So you can manage them like the way you manage containers, right? So you can have your unique tag, your stable tags. Just remember, you have to stay on target, right? So nothing really fancy here. We're able to use container registries the same way that we use container registries today. The user space tooling is all basically just bootc. It's a couple of different commands, things like upgrade, really just do a fetch of the current tag that you have defined and checks for any updated manifest. If it sees an updated manifest, it starts pulling that and can stage that for the next boot. Rollback back to the previous. Switch would be changing to a different container image. All right, so you'd be pulling a new container image. And then bootc install is the manual way without kind of any automation. I have used bootc install to file system when if you have like a cloud image that boots just like a regular Fedora image, the Fedora cloud spins. You can then, that is not a bootc implementation, you can use bootc install to file system in order to reboot it into, it'll basically kind of blow away /boot and set up an OS tree partition or an OS tree file system inside of your root file system. Seems really dirty to me, but it does work. And you can reboot into now your bootc based OS. This is just kind of showing what that looks like, right? So, we do that pull, and we can go to our different, it is still kind of an A/B transaction model. You can go, this has RHEL, but like, it's like you can go from like Fedora 41 to 42 to 43, right? Like you can kind of start to, it's kind of wild how much you can, how far you can go with some of this pattern. And then underneath it all, it's OS tree and ComposeFS. So this kind of gets what you're talking about, right? So what is OS tree? You go search the internet, and like their website says, Git for operating system binaries. It doesn't really mean anything. OS tree is a content addressed object store, right? So instead of storing /bin/bash, it stores it takes the hash and stores the content as the hash, right? And then it has a symlink or a hard link farm in order to map /bin bash to the content addressed hash of that binary. It's not a file system specific. It works like this. You have different types of objects like directory and file objects, commit objects, right? So a commit references a file system hierarchy that references the content objects in the OS tree repository. So when you upgrade to a second deployment, since you're using hard links, since you're using a file system, you can see here we've got bin bash, user bin bash, that is different. So we've got two different file objects we're duplicating. There's extra data there. But user bin true is the same. So we can reference the same content hash, right? So we can deduplicate a little bit, right? So we can save a little bit of space. Really what we're doing. Very complex system to save some space, guys.
I love Golden Corral, and this is dirty compared to Golden
Golden Corral.
Well, you see, it's only dirty if you've modified something in the working tree.
There you go. Yeah. That's good. That's good. I like that. Okay, so what is ComposeFS? So an opportunistically sharing verified image file system, right? Obviously, right? What more do you need to know? Okay, so if you ask kernel developers, do we need a new file system? The answer will always be no, right? Look at bcachefs. Look at how hard it has been for him to try to get that in the file system kernel. And I think it's like been kicked out at this point. I don't know. But yeah, nobody wants new file systems, right? I don't remember his first name. Riser, the guy who made Riser FS, went and committed some crimes, and now somebody has to maintain Riser FS in the kernel for 10 more years, right? So nobody wants more file systems. So what is ComposeFS? Well, it's a new file system. No, I'm just kidding. So it's not a new file system. It's user space tools. It combines OverlayFS, ArrowFS, and FS Verity. Is anybody familiar with ArrowFS? Okay. Anybody familiar with SquashFS? Okay, cool. More. Okay, so SquashFS was like never really perfect, but it was good enough. It was created, I think, by the guy who created the first ISO live CD image for Linux, Klaus somebody. Shoot. Anybody?
Klaus Finland.
The first live CD, Knoppix, was created by.
First?
No,
it was very close to it.
Oh, fine. Damn. My nerd card. Where's my nerd card? Okay, whatever. Nobody knows. So SquashFS isn't perfect. ArrowFS is designed to be a little bit better than SquashFS. So there is a new file system in the kernel. It's ArrowFS. It is like byte align. There's all kinds of like fancy features that I don't really care about. But it makes it better. It's basically SquashFS, right? It's like, let's take all of our file system, let's put it into a single file, let's be able to mount it and probably peruse it like a normal POSIX file system. So ComposeFS is kind of like our next evolution on OS tree storage, by basically combining these three things, trying not to create a new file system. It's basically the same thing, but it uses these other technologies instead and allows you to basically, okay, so we store the metadata for the file system in ArrowFS. So we have a very small ArrowFS that has all of our metadata and all of our hashes in it. And then we use FS Verity in order to do real-time cryptographic signature checking of the file system as the access happens. So we can detect any sort of changes in the underlying file system immediately, while also allowing for deduplication. Really cool stuff. I don't have the picture of it, but the developer of ComposeFS works for Red Hat, Giuseppe Scrivo. He had a cool kind of test where he looked at, what they're also looking at ComposeFS. So this is OS tree in ComposeFS. But what they're looking at it for is also they're trying to make it the underlying file system for containers, for Podman, right? If you think about when you pull containers, when you pull container layers, when you pull almost the same containers, two containers that were built on top of each other, you duplicate the layers, right? You have to duplicate all of that stuff, which then fills up your file system cache, because you have to duplicate all this stuff. ComposeFS allows you to deduplicate and cryptographically verify that you are able to deduplicate because it is the exact same file based on hash. And so, they're looking at it as a way to control the storage of your container runtimes.
So are you guys planning a graph driver?
Yeah, it would be it's a graph driver for
You
Podman.
get the entire file level, right?
Yep. Yep.
Oh, but I guess you're still having to effectively assemble the RFS in such a way that it's determinist as signatures void.
That's a big part of yeah. I don't know. I guess with Podman that would be happen at the pull time or something like that. I'm not entirely sure.
Yeah, well, you already have to do that like LVM direct, it is up to the implementation how the layer is persisted on disk.
Yeah.
It is.
Yeah. Exactly. Yeah. And so that's how ComposeFS would do it. Yeah. So that's about it. So, okay, let's look at a demo here. So, let's see here. Okay. Awesome. So
Scan.
what? It's not working?
No, we're losing the first few characters of your prompt because
No, it looks pretty good.
oh.
Yeah. We got all of it. Yeah, we're good. Okay. So if we were to just do freaking copy paste on a laptop. This is the first time in quite a while that I've tried to demo something on Linux. No comments about me working for a Linux company.
Shift insert your phone.
I don't know what's going on. Oh my goodness gracious.
No,
Okay.
just install KDE. No one sucks, and we all know it.
Okay, that's probably my solution next. So if we do a Scopio inspect, we will see, okay, let's scroll up and scroll down here. Okay. We have all the layers of our file system. So this is like the manifest file. This is when you pull a container, this is the first thing that you get. You get the manifest, which is a JSON of everything else you need to pull. As part of that, those layers have annotations of what's going on. They're like the commands that you would run when you create that layer. You can see here we have RPMs, right? So each layer, in this case right here, we've got all these layers are all individual RPMs, right? Kernel modules, NVIDIA GPU firmware. Okay. So now what we're going to do is we're going to build our base container image. So if we look at base, we look at container file, we are pulling from Fedora bootc 43. We're adding overlay, which we can do a find of overlay and base overlay. We're just adding a local registry conf file into our .d directory. And we're doing a lint. So if we do I swear I know how to use computers. Okay. We are just running normal Podman build commands, right? I mean, nothing really fancy here. We are tagging that. We're going to push it to our registry. And that's running on this box. We're going to push a lot of layers because, as we'll see, we have an enormous number of layers because it's deduplicated. The base image has already been run with not rehash, whatever I said earlier. Thank you, rechunk, and it's deduplicated a lot of stuff. So we can go look at that. I'm running Zot as my container registry. It's really cool. You guys should check it out. But if we go look at base here, we've got a vulnerability scanner. It's using Trivy, which is from Aqua Security. So it's running a container scan, it's seeing all kinds of vulnerabilities. That's cool, whatever. Who cares about those? So and then we can see all these layers. These layers have names, right? We've got Podman, Python 3, whatever, RPM. We've got sometimes where it kind of it batched up a whole bunch of RPMs and put them into a single layer, right? So we got 170 different components in there. We scroll down to the bottom here. We have our add of our directory and then our bootc container lint. So we just added 2 more layers to the end of this base container image. So nothing crazy here. Now, if we create our QCOW image, so if what we're going to do here is we're going to create a very simple config.toml, which is adding in my SSH key. This would be where you could, this is like a post install script, right? Sort of thing, right? Let's customize the container, the disk image that we're creating with a couple extra things. And then we're going to run the bootc image builder, which is actually a container as well, and we're going to specify our container that we're going to be creating. So creating the bootable disk from. So we've got to pull. Oh, wait a second here.
You have a lot of it.
I need to run this as root. Okay, there we go. Since I ran this demo earlier, testing it, it already has it pulled. So now we're doing the disk build. So this is like OS build. This is the OS build project doing the disk image build. It's building a QCOW image, which we can see right here. It's building a QCOW image of our bootc image that's specified that we pushed earlier called Fedora bootc base. So this will make our QCOW image on disk, and then we'll load that into we've got just libvirt running on this laptop, and so we'll boot it up from there. Any questions so far?
So you guys have already explored kind of swapping up the storage layer as an option to make, we'll say, things align a little bit better with OS3. The whole rechunking process as a way to try to get some semblance of Delta updates, just it does not sit well.
Oh yeah.
And so I guess that leads to the question, are you guys potentially exploring an alternate transfer method? You know, since you're already going through and doing things like the RFS that are indexed, since OCI layers are compressed tars, they're not seekable, they're not indexable in any way. Is that something y'all are exploring as some other way to deal with file contents? Something like going back to the old days, to make Mr. Zane over there a little bit happy, kind of like the way IPS handled file deltas.
We probably wouldn't be able to do very much beyond what container registries can handle today. So, you know, if you want to swarm container image files with like, you know, Dragonfly registry or whatever, you know, like maybe you could get some speed up by adding BitTorrent to your container registry pool or something like that, right?
I was surprised when I looked into bootc that the app initially that it was still using regular container layers, that it wasn't some other MIME type for a
oh, like an OCI artifact kind of style.
You can give any MIME type you want to the registry.
Sure.
There's even ways to do alternates to say, I published this container, but here's, I don't know, also this other artifact. That's how content trust works.
Yeah, I think we still, you know, I think the primary objectives of bootc are to remain as committed to the container ecosystem as possible. So, you know, your build process would have to adapt to your new MIME types, as well as your storage, as well as your deployment, right? So like you want to keep that, I think they want to keep that surface area as small as possible. But maybe in the future, I mean, OCI artifacts really have only taken off because of ML models, right? Because of these large language models, right?
Helm uses them.
And that was the very beginning. And for a long time, nobody supported OCI artifacts. And then, you know, Helm browbeat people enough into doing it, right? But yeah, I mean, how long did it take ECR or ACR to do those things in the cloud, right? You know, it's been a while, but yeah, now everybody does, right? Now it's like a normal thing. So maybe you could see that in the future, but I'm not aware of anything. Okay, so we've got our QCOW built, and now we can run it. if we do our little vert install here of our QCow, we can go see it over here. We got the console still. And so we've got our
Oh, great man, doing it on this just released version.
Fedora 43. Yeah. I was testing on Fedora 42, and then I was deploying everything with Fedora 43, and then I realized that something booted with Fedora 42, and I hadn't updated my tags. So it was a good test. Okay, so we've got Jason at 192, 168, 122, 128. Now what was that? 125.
Let's release it.
Um I don't know why. Oh, yeah, okay. My one password SSH agent is having issues. Whatever. Jason Jason was a password, Jason was username. So I was able to get into the system because I did that post install stuff. So now we can do boot sudo boot c status
That Pommel, what parsed that?
OS tree.
Oh, tree itself?
Mhm.
Okay.
Yeah,
And it did that at boot time, or did it do that at the image build time?
build time. So it laid down that OS tree to image. And then I was thinking about this earlier. I'm not entirely sure. I need to go look at that, but it must do some kind of thing where it can mount the OS tree for the post install script, essentially. Because it has to have the full file system there to do that work. So I don't know if it does that before it commits the OS tree commit or after and does a new one or something. I'm not entirely sure.
If you still want us to pull and push to work easily, it should be its own commit, but that doesn't mean that you can't. OS tree commits don't need to have that history.
Yeah. Yeah, correct. Yeah, it's not quite like Git in that sense, right? Yeah, so we've got our base. If we go and say we wanted to build a almost done here, if that's okay. We wanted to boot chttpd container file. Say we wanted to add HTTPD. We're going to create an index.html, but we're moving the index.html from var dub to user share dub because of our var problem, right? So we're going to build and push our new boot C HTTPD. So I'm back on my local machine in the bottom left here. I'm on the boot C booted system on the upper left, and I'm root on the right. So we're going to build a container with HTTPD and just a very simple index.html. And then we're going to push that up to our container registry. Most of the stuff already exists. That could be also because I ran this test earlier and I can't actually delete the underlying blobs from Zot without deleting the full storage, and I didn't do that. Okay, so now if I wanted to use this, if I do just boot C update, there's no update available because boot C base didn't have anything pushed to it. So I have to do sudo boot C switch to boot C Fedora base HTTPD. Is that right? Yes. And so you can see fetching layers 4, I only need 80 megs because I already had 67 layers. So it's only catching that last little diff there. And then now it's creating the OS tree commit on the disk. It's creating that next boot, setting up VLS, setting up all those items to boot in the correct order and all that stuff. So now queued for next boot. So if we look at status, we will see that we have the booted image as our base. Our staged image is HTTPD. We've got our digest, all that good jazz. And then now we can reboot. And if we go look at our system, you'll see that our grub will have 2 different entries, OS tree 0 and OS tree 1. That went way too fast, but OS tree 0 is the boot we want to get into.
So when is OS tree garbage collected, if ever?
Good question. I don't know. I would assume on a commit it would look at what's not needed anymore and get rid of it, but
Yeah.
that'd be where I would do it. VSOC is there, but with SE Linux enabled, you can't actually use VSOC. So I have to disable SE Linux, which is wild. But yeah.
Go on it to a while.
Yeah, yeah. Well, yeah, sure. Curl.
Changes visibility for that.
There we go. We now have an HTTPD server running on the system, and so hello from HTTPD bootc. So there we go. That's it. That's all I got. Actually, no, I have one more. Wait a second here. Wait. Okay. And then slideshow. Okay. So key takeaways. Mutable systems control intentionality of change. bootc uses container images for transport, OS tree for on disk format, but compose FS as well. Bootable images can be built anywhere. You can run container builds, declarative config to avoid etcd, and application data still needs to be managed. Nothing special. So punch it. Thank you so much, and engage. So,
Very much. And for all of our speakers, you are invited out.